And then chapter 15 is covering like gases, ideal gas law, heat. So chapter 15 is gases. And then 16, we have like engines and some entropy. And so our most important formulas from each section, this one right here is the like setup for a wave formula. It's like the equivalent of y equals mx plus b for a line. This is like the same setup for a wave. And then this one over here is velocity of a wave. And then this is velocity of a transverse wave, of transverse wave. But the second one is not as important as this first one. And this first one's important because it allows us to convert these equations between frequency and wavelength. And so we'll come back to these two equations. But this first equation right here is if a wave is closed at both ends, or if you have like a rod that's closed at both ends, or a pipe closed at both ends. And then this second one over here is if you have a pipe or something that's open at one end. So let's say this is open at both ends, and this is open slash closed at one end. Okay, and the way I like to remember these is I call it like rule of four. Rule of four. And I say if it's open at one end, it has to multiply up to 4. So you have 4L. And if it's open at both ends, so both ends would be 2. I call this 2L. And so then it goes to 4. If this doesn't make sense to you, you can ignore it. That's just how I remember it. And then these two, one more thing about this is we have fundamental frequency here. Fundamental frequency. Okay, and then from here we have like first overtone, and then etc. So second overtone would be 3 for this one. And it's the same for both of these equations, right? So this would be your fundamental frequency. This is your first overtone, second overtone. So note that the ends are different, but they're still called first overtone, second overtone, and so on. And so we also have here path difference for constructive and destructive. And these are for in-phase waves, in-phase. Okay. Those will make more sense, like if you see it in a question. But basically it's like the idea that if you have a wave, two waves that are in phase with each other, like this, their sum or their total would be like together. And obviously, like if it's flipped the other way, they would be destructive and like cancel each other out, right? So then we also have down here we have intensity. Okay, and intensity is measured in watts per meter squared. Um, and we also have this second equation, which is decibels. This beta is the same as, or like what they denote for decibels. Um, and essentially what decibels are is it's just the log form of intensity. You can see here that like you have this ratio here and then log. Um, so just know like if they ask for intensity, it's not the same as like decibels. It's this I right here. And you can convert between decibels and intensity by using this equation. This right here is what's called the reference intensity. So this is called the reference intensity. And what the reference intensity is it's the minimum sound like a person can hear. So it's basically like 0 decibels or whatever you would call it. So I'll write like 0 decibels right here. Okay. Um, and this equation, this one can also be used to determine like difference between decibels, but I don't think that's gonna be on the exam. Just know that like mostly you can convert between intensity and decibels using that equation. Um, we also have this beat. Um, I honestly don't really know much about it. Um, so yeah, I didn't see any on like the last two exams, so I think it's relatively not important. Um, but I didn't check any of the older exams. But we also have here, this one's important. This one is Doppler. Doppler. And if you remember, this is like if you have the person and you have like the train, and if they're like moving towards each other, your frequency increases. If they're moving away from each other, the frequency decreases. So we'll cover that more in a question later. But that's Doppler. Okay, and then for chapter 13, we have this equation on the right, on the left. And this is just density. Note that this right here is a rho. It's not a P, so don't get it confused with this right here, which is pressure. I guess, yeah, those two are pressure. This right here is a rho again. So that denotes density and not pressure. Um, these right here are for pressure. So this equation is just saying pressure is equal to force perpendicular over area. I think that one's pretty self-intuitive. And then we have this one right here, which is pressure is equal to, this is atmospheric pressure. So atmospheric pressure. And then this one is equal to density times gravity times height. And so this concept is essentially like if you have a cup or something, and the surface is like filled with water or whatever, you would use it to find like the density at the bottom of the cup or whatever. And so you have to add atmospheric pressure, obviously, right? Because there's like ambient pressure around the cup. So that's where the atmospheric pressure is coming from. And then also you have buoyant force right here. This is buoyant force. And buoyant force is equal to density times volume times gravity. And so an easy way to think about this, let's make like an extra page. So if we have like this cup here or whatever, and we have it's filled with some liquid. Let's just say filled with water. Filled with water. Um, if we then put like some object in, like normally it's some sort of ball. Let's put this ball in. This ball is going to displace an equal volume of water. So ball displaces equal volume of water. Okay. And what this equation is telling us, this force buoyant equal to density times volume times gravity, this formula tells us that the volume displaced, so volume displaced times the gravity times the density is equal to the buoyant force. Okay. And so essentially, when it displaces that certain amount of water, the amount of water equal to its volume, the weight of the water displaced is going to equal the buoyant force. So let's say weight of fluid displaced is equal to the buoyant force. This is the essence of the equation, and this is called Archimedes' principle. Okay. Hopefully that makes a little bit of sense. I found these really confusing when I took the class. But yeah. Okay. So that's chapter 13. Chapter 14 is thermo. So these equations at the top are going to be your conversions. Okay. So we have like between Fahrenheit and Celsius, between Celsius and Fahrenheit, Kelvin and Celsius, and Celsius and Fahrenheit again. Or I guess 1 degree Celsius is equal to 9/5 degree Fahrenheit. So these can sort of be used interchangeably, but these are going to be more useful, right? So then in this second, these two equations right here, this is your linear expansion equation. Linear expansion. Okay, and then this one is what's called volumetric expansion. Okay, and that tells you, linear expansion and volumetric expansion tells you that when you heat something or cool something a certain amount, delta T, that object is going to expand. If it's like a linear object, it's going to expand linearly. If it's like a box, so this would be for like a box. This is for like a wire or something like that. These things tell you like how much something is going to expand or contract. This one, I'm not exactly sure what it is, but I don't think it's that important because I didn't see it anywhere. These things are your like heat exchange. So this is heat for a liquid. That's like how much heat is required to raise something X number of degrees or whatever. That's where this delta T is coming from. That's where this mass is coming from. And then C is your specific heat, right? This one right here is for fusion, which is melting, or evaporation, so boiling, however you want to say it. And so you can see LF, latent heat of fusion. You have this 3.34 times 10 to the fifth value, which is this L right here. And then vaporization, you have this value for this L right here. So this one tells you phase changes. This one tells you like if it stays the same phase, how much is required to raise that mass X number of degrees. This one tells you like heat according to how much the temperature changes. Sorry. If you have, it's in this question. Let's see. I think this will be a little bit more clear. Okay. So it tells you like the energy transferred by heat through the glass. Like how quickly, so I guess how quickly it's transferred. But we'll look at like how to apply that question or how to apply that formula here. And then also we have this one, which is also like the emissivity of the heat. And then that equation we'll also take a look at in a problem. But these two, mostly you just plug stuff in, so they're relatively simple. And then we also have chapter 15. So if any of you guys have taken chemistry, it should be pretty familiar. We have ideal gas law here. Since we're dealing with gases, we use this R. So ideal gas law. Okay. We also have kinetic energy of a gas. Okay. And then you can see that these two are very similar. This one is kinetic energy of an individual particle. Okay. So they look very similar, except that this one has this K here instead of the NR, and this K is Stefan Boltzmann's constant, which is given to you right here. Okay, and then this one right here is the root mean square velocity. This one is also, you just plug the numbers in. I don't think you really need to like understand what it is. But yeah. Okay, the rest of these are not that important. Like this one's not that important. This one's not that important. This one is your first law of thermodynamics. Thermodynamics. And then this one is important. And that's just saying work is equal to pressure times your change in volume. And we'll see how that's applied in questions. I think that's a little bit easier. Okay. And then we have engines. The engines are also, you just plug stuff in. So this one right here, we just have work is equal to heat. This one is like efficiency. And then, yeah, the rest, this is just a Carnot engine, saying that they're like proportional. This is just also the efficiency of a Carnot engine. Um, but yeah. Okay, so let's go over the exam now. Um, okay, so question one, we have a pipe with length L. It's open at one end and closed at the other end. So at one end, so we know we'll be using a 4 equation, or that we'll be using, so by a 4 equation, I mean this equation right here, the one with the 4 in it. So this, and so the wavelength of the first overtone standing wave in the air in the pipe is 0.6 meters. So instead of given frequency, we're actually given wavelength, so 0.6 meters. And we're asked what is the length of the pipe. Okay, so what we have to do here is we actually have to convert between frequency and wavelength. So we'll use this formula right here. So velocity is equal to frequency times, or gamma times frequency. Okay. And so gamma is equal to velocity over frequency. Or frequency, we also have frequency is equal to velocity over gamma. Okay, and so we'll plug actually the second one in, and we'll say this, velocity over gamma is equal to velocity over 4L. You can see here that the velocities cancel out. We're actually missing the n in the equation. This is just n times n times n. And so now you can see that it's 4L over n is equal to gamma. Okay, and so now that we have this, we can just plug everything in. So we're told first overtone, right? So we'll go here and looking at our ends here, this is fundamental frequency, right? So we'll take the second one, which is our first overtone. So that means n is equal to 3. So gamma is equal to 4L over 3. Gamma is this 0.6 meters. So now we have 1.8 meters is equal to 4L. So L is equal to 0.5445 meters. All right, so that's question one. And so two, we're told a point source of sound waves emits uniformly in all directions. If the sound intensity level at a distance of 5 meters from the source is 80 decibels, what is the power output of the source? If you remember, I said earlier that intensity and decibels is not the same thing. When you have questions like this and they say sound intensity, they refer to decibels. When they say just intensity, they're referring to like the watts over meter squared. And so that's important because we're asked to solve for power output, right? So we'll be using this equation right here. So intensity is equal to power over 4 pi r squared. Okay. And so to actually solve for this this intensity right here, we have to use this equation. This beta is equal to 10 decibels log I over I naught. Okay. And so we'll just do this, plug everything in. This 80 decibels is equal to 10 decibels log I. And then our I naught is actually given right here. Again, remember the reference intensity. So it's 10 to the negative 12th. Okay. And so we have 8 decibels is equal to log I over 10 to the negative 12. And if you remember the log rules, this is just assumed to be base 10. So now we have 10 to the 8th is equal to I over 10 to the negative 12. And so we multiply both sides by 10 to the negative 12 times 10 to the negative 12. So these cancel out, and we're left with I is equal to 10 to the negative 4. Okay, and so now we're going to plug this in over here, and we say 10 to the negative 4 is equal to power over 4 pi r squared. Let's get rid of this arrow and move this over. And when we multiply r squared, which is we're going to leave as 5 meters, so 10 to the negative 4 times 4 pi times 5 squared is equal to power. When we multiply all of those together, that should give you the correct answer. It's 4. All right, so that's number 2. Okay. And so number 3, we're told that there are two sources of sound waves, waves A and two sources of sound waves, A and B, are emitting in phase sound waves of the same wavelength. Source B is 0.3 meters to the right of source A. Point P is 0.5 meters to the right of B. What is the largest wavelength of the sound waves for which the interference at point P is destructive? Okay, so since we're looking at destructive, and because we know that they're in phase sound waves, we just use our destructive interference formula, and we're also told that we want the largest wavelength, right? So we're just going to let n equal 0. So we have path difference is equal to n plus 1/2 gamma. Okay, in path difference, so between A and B is 0.3 meters. 0.3 meters, and remember we said n is equal to 0, so now we just have 1/2 times gamma, so gamma is equal to 0.6 meters, and that's our answer. Okay, so number 4 is a Doppler question. So we're told a train's whistle is emitting sound waves with frequency 600 hertz. So frequency source is equal to 600 hertz. Train is traveling due west toward a listener with a speed relative to the air of 40 meters per second. So that's already drawn in the diagram. The listener is also traveling west with a speed relative to the air of 10 meters per second. So take the speed of sound in air to be 340 meters per second. What is the frequency heard by the listener? Okay, so if you remember, we always said that the right is positive and the left is negative. We can also intuitively say, based on our knowledge of how Doppler works, that frequency should increase, right? So we're told we have the 600 hertz. So we can eliminate answer choices A and B. But let's go to our formula sheet. So we have Doppler right here. So frequency listener is equal to velocity plus velocity listener over velocity plus velocity source times frequency source. Okay, so if velocity is equal to 340 meters per second, then we have 340 meters per second plus the 10 meters per second for velocity of the listener, and then 340 meters per second plus velocity of the source, which is 40 meters per second, so plus 40 meters per second times the frequency of the source, 600 hertz. Okay, and so when you plug that in, you get, these should be negative, right? Negative and negative. So you should get 330 over 300 times 600 hertz. Okay, and when you multiply that out, that gives you 660 hertz, which is our correct answer. Okay, so number 5, we have a rock suspended from a light string immersed in water. So this is an Archimedes principle question. Okay, so we have, let's just write out what we know. So we have rock, 2 kg, volume, 5 times 10 to the negative fourth meters cubed, and it's totally immersed in water. Okay, so that means that it's more dense than water. What is the tension in the string? Okay, so we're just going to take the volume displaced, and then that is going to be, well, the volume of the water, the weight of that volume is going to be the buoyant force, right? So we'll take force buoyant is equal to density times volume times gravity. And so the volume displaced is going to be this, 5 times 10 to the negative fourth. So 5 times 10 to the negative fourth meters cubed. And then of water, so 1,000 kg per meters cubed times gravity, 9.81 meters per second squared. So when we plug that into our calculator, we get, let's see, we get 4.905 newtons. So this is the buoyant force. So this is going to be pushing up against the rock and supporting it, so decreasing the tension in the rope. So we know that before, just the rock without, like if it's not in water, we know the weight of the rock is mass times gravity, which is 19.62 newtons. And so we subtract the buoyant force from that, and that gives us our answer, 14.7 newtons. So yeah, that's 5. So number 6 is also a Archimedes principle question. So we're told that the object has mass 0.5 kg, and it actually floats in water with half of its volume submerged beneath the surface of the water. So that means that the weight of this rock, or weight of this object, is equal to the buoyant force, right? So weight object is equal to buoyant force. Buoyant force. All right, let's also draw a little picture here. Okay, so it looks like that. Okay, so the weight of the object is obviously mass times gravity. So 0.5 kg times gravity is equal to the buoyant force, which is density times volume times gravity. But this volume here, in this generic equation, we can actually say is 1/2 volume object. Okay, and this density is going to be the density of water. Density water, and our gravities are going to cancel out. So that leaves us with this 5 kg is equal to density H2O times 1/2 volume object. You can see that what we're solving for, the volume of the object, appears right here in this equation, which is why it's useful to have it that there, replace it like that. And so we can solve from here and say, 0.5 kg over, let's move this over here. Okay. 0.5 kg over density water, which is 1,000 kg per meter cubed. And then this amount would be equal to 1/2 volume object. We can see that it's 0.5. Would be what we get when we multiply or divide everything out. And then you multiply by 2, and we're left with 1 times 10 to the negative 3 meters cubed is equal to volume object. Okay, and then that is our answer. Okay. And then we also have 7. So we're given a barrel containing a thick layer of oil, a 0.08 meter thick layer of oil with density 500 kg per meter cubed floating on water. That is 0.2 meters deep. What is the gauge pressure at the bottom of the barrel? Okay, so we would have a gauge at the bottom, and then looking at our equations, it would be this one right here. So pressure atmosphere plus density times gravity times height. They always ignore this pressure atmosphere, and it's always just this times density times height. Density times gravity times height. And so we can just solve for each one of these individually. So with oil, we would say pressure oil is equal to density 500 per meter cubed times gravity times height, 0.08 meters. And so when we multiply everything out, 392.4. And then let's do the same thing for water. So we have 1,000. Okay, and then you add these two together. And that gives you 1569.6. Okay. And so maybe you're tempted to like make this 0.08 plus 0.12 for the density for the height of the oil. but don't do that because that would be assuming that the whole barrel is oil, like the whole 0.2 meters is oil. So make sure you break them down into individual sections. Don't like assume that since this oil is actually like a height of 0.2 meters, that this becomes 0.2 meters. So it's just 0.08, and then this one is just 0.12. Okay, so that's number 7. And then number 8, so we're asked to find the final temperature of the contents of the glass after thermal equilibrium is reached. So this is a Q equals MC delta T question. Okay, and then we're actually given the masses in grams, and so we're gonna have to convert those to kilograms. So this just becomes 0.120 kilograms. So wine mass is equal to 0.12 kilograms, and then the ice cube is equal to 8 times 10 to the negative 3 kilograms. Okay. And we're told this initial temperature is 0 degrees Celsius, and this initial temperature is 30 degrees Celsius. And so we're tasked with finding the final temperature of the contents of the glass after thermal equilibrium is reached. Okay, so if we imagine like the cup, like let's draw it. Oops, that's a horrible cup. Okay, so let's pretend that this is like our ice cube and it's floating in the wine here. Okay, so the heat is going to flow from the wine into the ice cube to melt the ice cube and raise its temperature. So that's going to be important for like our sign conventions when we set everything up, right? So we can say that basically the heat wine is going to be negative, right? Because heat is flowing out of the wine and into the ice cube. And the ice cube heat is going to be positive. So Q ice cube. That should make intuitive sense, right? Like if you're melting something, you need energy to melt it. And it has to come from somewhere. It's coming from the wine, obviously. And so when we set up our equation, so we'll say Q, we also have this one, Q equals MLF, right, for the ice cube. So on the left, we'll make this one ice cube. So MLF plus MC delta T is equal to just MC delta T for the wine. Okay. But since the heat is flowing out of the wine, we have to be careful with our signs. And we're just going to call this negative. So let's do this. Let's MC delta T is equal to negative MC delta T. Okay, and then from here, we just plug things in. So kind of running out of space, but let's say for the ice cube, if we look at our LF value, it's right here, 3.34 times 10 to the 5th. So we have 8 times 10 to the negative 3 kg times 3.34 times 10 to the 5th. I think it's joules per kg. Yep, joules per kg. Joules per kg. Let's actually move this. Let's start a new page because I think we'll need the space. So paste. Okay. So here we have this is fusion ice cube, right? And then we have MC delta T of the ice cube. So 8 times 10 to the negative 3 kg. So that's M times C, 4190, because now it's water, times delta T, which it goes from temperature final minus temperature initial, which is 0 degrees Celsius, right? Okay, so when we multiply everything out, we're then left with 2672 plus 33.52 times temperature final. And then on the other hand, we had this negative MC delta T of the wine, right? And we had this negative 0.120 kg times the C of the wine, which is given in the equation, given in the problem. It's actually 4,300. And then we have delta T, so T final minus T initial, which was 30 degrees Celsius. Okay, and let's multiply everything out. So we actually have 516. Okay, and when we move the negative over, we have this negative 516 temperature final plus 15480. Okay, and on the other side of the equation, okay, and from here, all we do is just solve for TF. Okay, so 516 plus 33.52. Okay, and then from here, you just divide and you get temperature final is equal to 23.3 degrees Celsius. All right, so that should be our correct answer. Let's go back here and yep, it's right there, 23.3 degrees Celsius. Okay. So that's number 8. And then let's do number 9. So glass window pane with thermal conductivity 0.8 in a home is 0.5 centimeters thick and has dimensions of 1 meter by 1.5 meters. If the indoor temperature is 25 degrees Celsius and the outdoor temperature is 0 degrees Celsius, how quickly is energy being transferred by heat through the glass? So we had this equation, which comes from right here. Okay. And then thermal conductivity is our K. And so we can just plug everything in. It's actually super simple. 0.8 watts per meter Kelvin times 1.5 meters squared from our area. So dimensions 1 meter by 1.5 meters. And then times TH minus TC. So 25 degrees Celsius minus 0 degrees Celsius over L, 0.5 centimeters. Make sure you convert this to meters. So 0.5 times 10 to the negative 2 meters. And when you multiply everything out, that should give you the correct answer. Which is 6,000 watts. Okay, perfect. That's number 9. And then 10 is going to be the one that uses Boltzmann's constant again. So this one right here. And we're going to be using this equation. And note that these temperatures need to be converted to Kelvin. But other than that, you just plug everything in. So let's plug in the area times the emissivity, and then times this sigma. Which we can find, let's see, where is it? Oh, it's right here. Okay, so 5.67 times 10 to the negative 8th. And then we have, let's just go ahead and convert to Kelvin. So it's going to be 150 plus 273, which is 423. And then 25 plus 273, which is 298. So we'll have 423 to the 4th minus 298 to the 4th. Okay, and then you'll multiply everything together, and that should give you the correct answer. So it gives you 0.68, which is close enough to this. Okay, so that's 10. So number 11 is going to be a volumetric expansion question. So we'll take that equation, which is right here, volumetric expansion. So delta V equals V naught beta delta T. Okay. And so we're told that we have a glass flask that's completely filled with oil. You heat it to 140 degrees Celsius. What volume of oil will overflow from the flask? So we'll just calculate the volumetric expansion of the gas and then the volumetric expansion of the oil. So let's start with glass right here. Okay. And so let's see, V naught is equal to 400 times beta, which is our coefficient of volumetric expansion. So for the glass is 6.5 times 10 to the negative 5th times delta T, which is 120. So when you multiply those together, you get 3.12. And now we'll do the same exact thing for the oil. So the volume of the oil is also 400 centimeters cubed. But the coefficient of expansion is this 1.3 times 10 to the negative 4th. And then the temperature is the same. And this is going to give you, when you multiply it out, 6.24. From here, you'll just subtract and you'll take the difference, which is 3.12 centimeters cubed. And that's your answer. Okay, so that's number 11. And so number 12, we have three materials, and we're trying to find which one has the largest latent heat of fusion. So if you look at your formula sheet, you have latent heat of fusion, which is right here for water. You can see that the units are joules per kilogram. So that means that when we look at our materials A, B, and C, we'll just be finding joules per kilogram, which means we'll be taking heat over mass, right? So this is 200 over 4, so 200 joules over 4 kg is 50. B is 300 joules over 5 kg, which is 60 joules per kilogram. And then C is 300 joules per 6 kg, which is 50 joules per kilogram. Okay, and obviously then it's B. Okay, so looking at number 13, we're told a certain quantity of an ideal gas undergoes an isochoric transition where its volume remains constant and its pressure increases. What can be said about the temperature of the gas as it transitions from point A to point B? Okay, so if you look at like your ideal gas law, okay, you can see that if you have volume remaining constant, but increasing pressure, what you'll have on the other side of the equation is increasing temperature, as you're not adding any more moles of gas, which is your N, and your R is a constant, so it's not going to change. The only things that typically are going to change are going to be your pressure, your volume, or your temperature. So that means that the temperature increases. So that's number 13. The textbook has some good explanations or good definitions for like what isochoric is, adiabatic, all of those things, all of the expansions. That's probably pretty useful to go and read. But yeah, that's number 13. Okay, so 14. We have two monatomic ideal gases in thermal equilibrium. One consists of a light element helium, whereas the other consists of a heavy element argon. What is true about the average RMS speed of atoms in these two gases? So if we look at our formulas, we have the RMS right here. So let's write out the formula. Okay. So if we have a heavy element, we have a larger mass, right? So you can see in this first equation, you have mass on the bottom, which means that mass is inversely related to velocity, which is where you're going to get this from, where the lighter atoms move faster than the heavier atoms. You can also think about this using, like, I think you can think about it using this equation right here, which is your kinetic energy of an individual particle, where again, when you have a higher mass, the velocity is going to decrease if they have the same average kinetic energy. So yeah, that's 14. 15, we're told, given the pressure volume diagram below, what is the total amount of work done by the gas on its surroundings as it transitions from A to B? So it's going this way. And work is always equal to area under the curve. Work equals area under the curve. Okay, so work is this, right? So all we have to do is find the area of the box, and since the pressure and the volume decrease from here, like from point A to point B, you can imagine it as like if you have a big square and it's being compressed down into like a smaller square. Obviously, it's not going to be doing work. It's going to be the surroundings that are going to be like compressing the box down. Um, so that's where we're going to get this negative sign from, because it's actually losing energy. It's doing negative work. I guess you can think of it that way. But so to find your area under the curve, we're just going to take this pressure 2. So pressure 2, 6 times 10 to the 5th. And you're going to take this difference in volume, which is just 1 meter cubed. And that should give you your answer. Right? And that's your answer right there. The reason why you don't take pressure 1 because it's not like there's no area under this pressure 1, right? So that's why you take pressure 2. Okay, so 16, we're told 3 moles of a monatomic ideal gas undergo constant pressure expansion in which the temperature rises from 100 Kelvin to 200 Kelvin. By how much does the internal thermal energy of the gas increase during this process? Okay, so internal thermal energy is just going to be this kinetic energy of the gas. So we'll just have 3 halves nRT is equal to kinetic energy. Okay, and so then when we multiply everything out, times 3 moles times 8.314 joules per mole Kelvin times our temperature change, which is 100 Kelvin. That should give us the correct answer. Okay, so that's 16. And so 17 is our first look at engines. So we're told an engine operates with efficiency 0.60 and it draws 1,000 joules from its high temperature reservoir. So QH is equal to 1,000 joules. In each cycle, what is the magnitude of heat rejected into the cold temperature reservoir? So we'll just go and look at our formulas. Since we're given efficiency, we know it's going to be this equation or this equation. And because we're not told it's a Carnot engine, we can safely assume we'll be using this top equation. So if we say over QH is equal to 1 minus QC over QH, looking at this, we're not told work, so we can just use the second equation, just this QC over QH. Okay, and now we have 0.60 is equal to 1 minus QC over 1,000 joules, which is 0.40 when you move the 1 over, negative QC over. Okay, and when you move the negative over and the 1,000, you get 400 joules. It's equal to QC. And that's your answer. Okay. So 18. So given an isothermal compression of an ideal gas, what can we say about the entropy S of the gas as it transitions from state A to state B? Okay. So this one's a little bit more tricky. But in isothermal compressions, we don't have any change in temperature. But that means, so let's just look at our PV equals nRT. So we have this decreasing volume and increasing pressure. But when it comes to gases, if you have like a bigger box versus like a smaller box, okay, in the bigger box, the particles have like more places they could possibly be, right? And so you, in a sense, have like greater disorder in the larger box. Whereas in the smaller box, the particles are much closer together. And so there's less disorder. You can also think about it as like you keep pushing it this way, keep increasing pressure, decreasing volume, you'll get like some sort of solid, right? Where this is obviously the less entropic state, so less entropy. And this is obviously the more entropic state. Okay, so that's one way to think about it. That's one way to get this. It decreases. The other way to think about it is that as it moves this way, you're technically losing temperature, or technically losing heat, because it's not like the pressure is compensating for the heat loss. It's actually the volume. So as you're like decreasing the size of the boxes, you're actually slowly losing heat, but maintaining the same temperature, if that makes sense. But yeah, I think this explanation makes a lot more sense than thinking about it as like heat exchange. So that's 18. So 19, again, we have an engine. So we have a high temperature reservoir of 800 Kelvin and a low temperature reservoir of 200 Kelvin. We're told the engine performs 100 joules of work. And what we're tasked with finding the amount of heat drawn from the high temperature reservoir in each cycle. Okay, so this amount of heat is going to be QH because it's from the high temperature reservoir. And since we're given just this TH, TC, and work, we just hunt for an equation that relates those things together. So right off the bat, like this one looks pretty good. This one looks pretty good too, because we have TC over TH. But if you look at this formula, you can get there, right? You can get to QH, but you can see that just using this efficiency is one step shorter than going through this ratio. So let's just set up the efficiency equation. So E car naught is equal to 1 minus TC over TH. Okay, and so when you solve for it, you have 200 over 800. So 1 minus 200 over 800 is equal to 0.75 efficiency. Okay, and then we'll use this equation. So E W over QH, E is equal to 0.75 is equal to 100 joules over QH. And when you multiply, you get 133 joules. Okay, so most of these engine questions, you don't really have to know how they work. Just know how to like use the formula. Most of them you just plug stuff in until you get to like the right answer. I don't think they're like that difficult. But yeah. Okay, and our last question, number 20, an adiabatic process is one in which no heat enters or leaves the gas. If a gas undergoes an adiabatic transition and its internal thermal energy increases, what must happen to the volume of the gas? So since it's asking about this heat entering or leaving gas, this is actually hinting at the first law of thermodynamics, which is this equation, and this is internal thermal energy. Q is equal to heat. I guess that actually should be capital Q, right? So Q, and this is equal to work. Okay, so if we're saying no heat enters or leaves the gas, we're just saying delta U is equal to negative work. Okay, and if you also look at your formula sheet, you'll see work is equal to pressure times change in volume. Yeah, it's right here. Work is equal to pressure times change in volume. And so let's write this down. Okay, so this equation should make like logical sense. Because again, if you think about like a box, right? The only way that this box does work on something, where we define work as like being able to move an object, right? Is if this box expands. So the key point here is that it's related to volume. Work is related to change in volume, and not necessarily pressure. And so when we take this and we have increasing internal thermal energy, increasing internal thermal energy, that means our delta U is going to also be increasing, or our delta U is positive, right? And so the only way to get a positive delta U is to make this thing on the right side of the equation positive also. And so since we have work is equal to pressure times delta V, the simplest way to make work negative, and so make this, if we say, if we want to make work negative, we'll have like two negatives, right? So it'll be a positive. The only way to make this work here negative is to have decreasing pressure. I mean decreasing volume, right? So if volume final is less than volume initial, then delta V is less than 0. And so that's where you're going to get this decreasing volume from. So because you need this negative work right here to get the positive delta U. So yeah, this one's probably the most confusing question. But yeah, that's it for exam for 2024. Good luck on Thursday. Good luck on finals. Yeah, I'll see y'all around.